Yeah. So when they asked me to come here and give a talk, I was like, well, what do you want to what do you want me to talk about? And they said, well, talk about how you got to be who you are. And it's like, oh God, I can't think of anything more boring. Um, so I've mostly going to be talking about what I'm doing now. I've actually just sort of retreaded a talk that I did for JPL just before Christmas. Um, but just as kind of a prelude, yes, I really am from Calgary. Some people seem to question this. Um, that's my dad and my grandfather. My grandfather's farm just east of Calgary. That's my grandfather again with oats and the rest of it. That's my dad, downtown Calgary, when it looked a lot different than it does today. Um, let's see, that on the right, that's my grandmother in Banff. My grandparents used to manage what is now the Mount Norquay Resort. My grandfather did the first ski lift in the Canadian Rockies, which was literally a pickup truck with a tire ripped off and a rope wrapped around the hub. But it worked, and it was mostly non-lethal. If you've ever used rope tows, they're spectacular. This is, I think, the most popular poster sold at the White Museum in Banff. And interestingly, this guy right here is my Uncle Gordy. And he gave me my first slide rule and my first real physics book. And then he went on to get a PhD in civil engineering, and I thought, oh, that is really, really cool. And I always thought the world of him. He's really a great guy. Sadly, no longer with us, but really, really cool. 1992 was kind of psychotic for me in Banff because everybody was wearing this T-shirt for the 75th anniversary of the Banff Winter Festival. Psychotic because Miss Banff was my mom. And wandering around town with your mom's picture on everybody is a little weird. It's a little weird. This is the only picture I've got of me here. So my mom insists that I'm 14 in this picture, and I think I'm probably more like 15. I don't know. So this was on the sixth floor of the Science B building. I was working for a bunch of physicists, and sort of follow-on echoes of that group are still there. Still doing work in upper atmospheric physics. Fairly strong group. And what's behind me is the computer that I was writing software for. There weren't many of us who were just writing software for it. This thing right here is a PDP-8, and it had tape drives, and just off to the side here was the big analog tape drives for the signals that came off of the satellite, and we could get generate images on the satellite on this screen that's like right behind my head. There's a paper tape reader and deck tapes, and there's a very fancy display off on the side here. The PDP-8, this PDP-8 was a big one. It had 8K of memory. So this thing has less compute power than a smart card. And that's always been kind of a touchstone for me. It's like, okay, if you can do satellite data analysis on what is now a smart card, if you've got a real processor, what the hell can you do? And one of the things that I think of as a kind of a tragedy these days is if you look at these multi-gigahertz processors we're using, at the way we're just pissing them away. You just look into what when you're running a web browser and it's doing HTML and JavaScript rendering, it's blowing so much energy on something really, really simple, it's just sort of a world kind of out of balance. But it was a great time. I mean, I was here for a total of 7 years, 3 years in high school as an employee, and then after that, then I actually signed up as a student. I sort of made the mistake of too many courses. One of the weird things about my period here as a student is that I technically didn't graduate correctly. I hadn't taken, and one of the stories that I didn't learn until like some time later was that I didn't actually fulfill the requirements of the degree. And the registrar was actually told Anton Collin, who was the head of the department, and he like exploded. And he all made it just the right things happen, and I never found out about it for years. But I had just taken too many courses in my major. Hadn't taken enough, anthropology courses, whatever. It's like, please let me do something that's actually useful and fun. I mean, for me, the reason that I've lasted so long is that this stuff is like more fun than anything I can think of. Then after here, I went to a place called Carnegie Mellon University. This is the main building of the CS department. These days, the CS department at Carnegie Mellon has 15 buildings. So imagine this building times 15. Well, some of them are smaller than this building, but they're mostly pretty darn big buildings. They've got one building that is the planetary robotics building. Bonus points. And a good place to wander around. I only ended up there by accident, but that's another story. Then I spent an awful lot of time at this place, Sun Microsystems. My office was, for a lot of years, was see where these guys are standing. You go through that door, down a long hallway, up some stairs. That was me for a decade. And this is now Facebook Galactic Central. But enough of that. There was then, all the stuff that I did with doing Java. I'm not a programming language guy. People want to get me in debates about programming language design. I like to have tools to get things done. And Java for me was always a tool for getting stuff done, it wasn't like a PhD thesis topic in how to make a cool programming language. It was all about how to get things done. And in many ways, Java has been successful because it wasn't trying to prove a particular point about, it wasn't like somebody's PhD thesis topic. It was a fairly blue-collar guy just trying to get his job done. And then of course it exploded, and I'm sure you folks have all been subjected to that and tortured by it, and I certainly hear it from my kids. The fact that it's became the sort of advanced placement core curriculum in U.S. high schools completely doomed me as a father. It was just a really, really bad thing. The way it's been taken up is just stunning. Every cell phone in the world has a Java runtime in it, even the ones from Apple. Although it's in the SIM card on the Apple machines. Like every financial transaction on the planet goes through a piece of Java code. And during Y2K, I'm probably one of the few people in the world who could say that I had the potential to single-handedly destroy the world economy. And I guarantee you, New Year's Eve, 1999 was stressful. Glad to not be there anymore. Glad that it's now somebody else's problem. When you do software at university, right? You're writing a piece of code. You got to get this problem, and it just has to work once, right? And it's a completely different skill to get software that works and works and works and works. Something that, and all the structures around building stuff that you can depend on. If you were building software for a car that you had to get into and drive at 60 miles an hour. You think about software differently, when, your life is on the line, your bank account's on the line, your kids are on the line. It's just really, really different. And it's not bad and boring, it's just different. And in many ways, it's a lot more exciting. So with that as prelude, what I would like to do is talk about what I'm actually doing now, because I think what I'm doing now is a lot of fun, and you guys would probably get a lot more out of that than pictures of my dad. So these days I work for a company called Liquid Robotics, and we make this. It's an autonomous robot that can wander the ocean. In many ways, it's a lot like a Mars rover. And in fact, this set of slides was actually I gave an invited lecture at JPL, because I used to be I was a kind of a distant visiting scientist / advisory board member at JPL for a bunch of years. So I was reasonably intimately aware of what goes on in the guts of the Mars rovers, and both the interesting bits and the embarrassing bits. And so if you look at the wave glider kind of sideways, it's a lot like a Mars rover or your Europa rover or whatever. You just don't have to like strap it to a rocket and send it somewhere. And so it's so why would one want something out there? It's for me, one of the things that always helps me get engaged in something is if it's for some interesting reason, right? And we're critically dependent on the ocean because it drives the atmosphere, it drives the food systems, and it's something that we know almost nothing about. And the data that we have is very sparse and very, very expensive. If you want to take a boat out into the ocean to measure water temperature, the kind of sort of scientific boat that can take you out any interesting distance costs about $150,000 a day to run. That's like the amortized cost of the boat, the fuel, the crew, the whole 9 yards. It's really, really expensive, and that's fundamentally why marine science is really, really hard. So what if we could make data dense and cheap? And you really can't fix things that are broken if you can't measure them. And so figure out how to measure them. So this robot is not your typical robot. It's like a Mars rover. It doesn't have the 7 minutes of terror. If you ever saw that video, when the JPL guys were planning that thing, I was down there. It was like and when they were describing what they were thinking of doing, I thought they were complete nutcakes, but it worked. Wow. But many hundreds of millions of dollars later, right? So this is what our robot looks like. It's a two-part thing. You can go swimming with it. It's interesting to go swimming with. So there's a part that floats on the surface that's kind of like a surfboard, and there's this strange thing that's on the end of an umbilical that's got all these wings that go across. And the float is on top of the waves and bounces up and down in the waves. It's filled with batteries and electronics, and it's got solar cells on the top. And this whole thing started actually with a guy named Joe Rizzi, who was one of the early guys at Fairchild Semiconductor. And then he became like a VC and whatever, and ended up with like more money than God, and a nice place on the Kona coast, and lawn looking out over the whales, humpback whales jumping off his lawn, and obvious question was, I can see them but I can't hear them. And so, being an electronics engineer, he did all the usual things that one would think of, after like 2 or 3 beers, like a long piece of wire and a microphone and a rowboat, and you drop it in the water and like, well, that's got problems. And you keep trying various things. And at one point, he decided what he wanted was kind of like an RC car for the ocean. And then he roped in a couple of his friends, a guy named Roger Hine and his dad, Derek Hine, to help him. And they, over a couple of years, came up with this rather interesting mechanism. And then I got hired a few years ago to do sort of next generation software for them. So how the thing works is there's the piece that floats on top, and as the waves go up, the float goes up, and that pulls this rack with all the wings up, and the wings are on a little hinge. And as it goes up, the wing does this. As it goes down, the wing does that, and there's just a little spring that sort of holds the wing in there. There's no electronics. There's no really complex control system there. It is literally springs and hinges. And as this thing sort of bobs up and down in the water, it generates thrust. So it generates about 700 pounds of thrust. And so we've got the motor that never quits. The thing will travel. We actually need not much in the way of waves, so we can actually make reasonable progress with only like 2 or 3 inch waves. But because the system is so simple, I mean, it's literally a floating part, a piece of that sinks with these wings. There's no active control anywhere except the rudder. This thing can be made extremely robust. So this thing will handle like scary weather. So there's electronics all over the thing. There's masts that typically have things like a weather station. You can get wave monitors. You can get sensors that scan downwards. You can put cameras on them. There are solar cells on top. You can tow things. Often if you're towing microphones, like you're doing marine mammal identification or something like that, you want to have very quiet and very it's easy to spend $10,000 on a microphone, and they're amazing microphones. And like I said, the only thing that moves that we really require is this little rudder that's right there. So most of our communication happens using the Iridium satellite network, and satellite networks are expensive. So in modern networking, people have is sort of like 100 megabits is like the slowest network you can buy, other than like your home DSL line or whatever. And if you're inside a data center, there's nothing slower than a gigabit. And I have to live with $1 a kilobyte and about 3 minutes for a kilobyte. And when you're encoding packets at 1/10 of a cent per byte, you really think about protocol encodings. I mean, if various standards like XML, right? XML has always made my head explode. It's one of the stupidest standards ever foisted on the, it sort of takes something that should take like 1 byte and encodes it in 100. And there's just no, I mean, it was stupid to start with. And when I see people doing XML over Iridium, it's like, and one of the things that's weird is that given the history of the Iridium satellite network, the government has this weird deal with Iridium that all of their traffic is free. So when you talk to people who do government-related things on the Iridium network, they go, "Why are you worried?" It's like, because I got to actually pay for it, and it really changes the way you think about networking, and in many ways it feels like I'm I'm on a PDP-8 again, right? You know, it's really kind of funny the way there's this sort of wheel in technology, right? You're always sort of back in 20 years ago as things get sort of reinvented, rediscovered. You take technology to some new place and the universe is just different. And it makes it always really interesting. So for us, we have different kind of durability issues, right? We have to deal with high seas. So for us, 20-meter waves, easy. 30-meter waves, yeah, that gets a little tight. Of course, 20-meter waves, that's 60 feet. That's pretty tall building. And we do those, no particular problem. 10-meter waves, we hardly even notice them. This is a wind chart from an event off of Australia not long ago, and this data point here is wrong because our wind speed sensor flattens out at 50 knots. Because you can't buy marine rated wind speed sensors for deal with higher than 50 knots. Why, I hear you ask? Because there are no ships that can survive beyond 50 knots, so why bother, right? You know, and so we've been in places where we know that it's gotten very close to 200 knots. We've been in, you know, Category 4 storms and come out alive. So we're you know, like in hurricane season, we are literally the only data source from the underside of the clouds, and that's where the action really is. Salt water, not a big engineering issue in Calgary. You know, growing up in Calgary was always kind of weird because I didn't actually see an ocean until I was somewhere in my 20s. And you know, I'd been to Vancouver, but you never really see like a horizon, right? And you know, whales and unicorns were kind of in the same category of mythical beasts. And you know, I had seen like narwhal tusks, so I could believe that unicorns could exist, right? But humpback whales, no, I don't think so. And oddly enough, sharks. We actually have to design for sharks. This is one of our guys after having been mauled by a rather large shark. And you can see from, you know, how far down the scratches got on the wings. They're sort of down there. His mouth was really large. And interestingly, he mostly just scratched the paint. These things are a marvel of material science. You know, lots of things that are technically fiberglass, but you know, the glass fibers aren't your normal glass fibers, and the resin sure isn't, you know, what you put on your boat. And there's, you know, lots of titanium and weird stuff. So they're fairly remarkable that way. But every now and then so this was the only place where we had an exposed cable that went around a hinge. On that particular one, a tooth nicked the cable and we lost communication with the rudder. So robot perfectly happy, talking to us, can't talk to its rudder, so it's just floating. Fortunately, the currents took it to Maui, and we went and picked him up. So what do you do with these things? They get used as weather buoys. One of the interesting things about these, so a weather buoy that'll sit out in the middle of the ocean is remarkably expensive. Not because the buoy is expensive, but the boat to put it there costs $150,000 a day. And you know, a round trip to the middle of the Atlantic is about 2 weeks. Do the math. And you have to do, you know, a maintenance visit on these things at least once a year. You except that what's been happening lately is that there's this big array of weather buoys across the equator in the Pacific that measures a lot of the El Nino effects and all of that. 2 years ago, Congress defunded the last maintenance ship. So there's only like a third of them still functioning. And, so they wonder why they get weather surprises. It's like, America. So we get used a lot in oil and gas. You'd think that's sort of surprising, but we can carry instruments around undersea oil fields. We can carry acoustic modems for communicating with instruments and subsea vessels of various sorts. The oil and gas industry puts all kinds of instruments on the seafloor, but also things like tsunami monitors. There are lots of people that care about tsunamis. Japanese high up there on the list of people who care. Tsunamis are really hard to detect because they're giant waves, but they're very shallow. They're rarely more than about 1 meter high, but they'll be like 1,000 meters wide. So if you're just floating there on the ocean, you can hardly, given all the other waves, they're impossible to detect. So what you do is you put on the bottom, on the seafloor, you put a gravitometer, and there's enough mass in a tsunami that it distorts the Earth's gravitational field by enough that you can detect it. So the gravitometer sits on the seafloor. So then how do you get the warning signal out of the gravitometer? Well, the standard practice is a really long wire, right? So you have a 1,000-kilometer wire from your gravitometer to shore. Expected lifetime of not very much, because it's the ocean. Stuff happens. All kinds of things happen that make cables break. So the vast majority of the world's tsunami monitors are talking to an open circuit. Whereas our guys can just sort of park over top and listen via an acoustic modem. You can't use acoustic modems because they're only good for about 4 or 5 miles. You can't get a long distance offshore. So we can send one of our guys out. They'll do donuts over top of the sensor for a few months. And every few months we'll send a new one out, and the old one will come back, and we'll scrub the barnacles off and give it a tune-up and trade them back again. And since they can install themselves, I mean, they're mostly just parked in the middle of the ocean, but you don't have to put them on a big expensive ship to carry them out there. You just heave them off the beach and they swim out there themselves. We do a fair amount of pollution monitoring. These things are really platforms that you bolt instruments onto. We do global warming studies. We do fisheries studies, a bunch of stuff off the Grand Banks that's entertaining. That's a blue-footed booby. They're really great for messing up solar cells, but got to give them a ride. So what am I particularly doing? So we've just done a whole new redesign of our robots, and we made the mistake of redesigning absolutely everything. All new software, all new hardware, new hull design, new. It's crazy. This new generation of robots looks a lot like the old ones. It's got a lot more power. This one's actually got a thruster that can help for breaking out of currents and that, but we still mostly get our thrust from the waves. Designed to work in fleets of thousands of them, and with much more sophisticated software. So the software on this new one has gotten kind of out of control. It's very good at doing things like dodging ships and staying out of trouble. And for this project, because the old one was really, it was quite a marvel, but the software was written on a microcontroller that had 64K, and it just barely worked, and it was quite amazing, but it was also quite primitive. So everything just started from the ground up. This is sort of the guts of the control unit, and the heart of it really is this, which is almost literally a cell phone. It's somewhat reworked because we have to have different kinds of interfaces. All of these boards up here, these are all the power supply. Controlling power on one of these things is really dicey, because you need to be able to handle high power situations, low power situations, turn individual things on and off, be able to measure the power flows, being able to deal with crud that happens. And it's a really an amazing piece of sort of defensive electronics. But in its heart, it's a cell phone. It's about the same power as like a Beagle board or like a Raspberry Pi. You know, think of a Raspberry Pi with a power supply on steroids and a lot of serial lines. So this is tied into a network architecture, most of which I will not say very much about. So the wave gliders talk usually via satellite. If they're close to shore, they can use cell phone. But most of the time, I mean, there's no cell phone coverage on 99.9% of the ocean. So we use Iridium there, and that talks through satellite ground stations to this sort of redundant cloud system that I built a year ago. This sort of combinations of redundant data cluster nodes, which is what sort of stores all the telemetry that we get, and then web apps that are used to distribute either monitor the craft or distribute data to customers, or drive desktop apps. So like one of our, whoops, where'd it go? This is one of my desktop apps. So this is a live feed from, so this is the Big Island in Hawaii. And if you ever go to the Big Island on a vacation, you probably stayed down here, which is the Kona coast. We're up here in a container port. It's a TSA secure zone. Our engineering building is. Oops, right there. All those squiggles are GPS noise, and so that's where we're located. So this is streaming live data off of through that network, and if you watch, you'll see this guy is slowly chugging along. One of our robots who's, I don't know where he's going, but he's going. There's just a couple that I'm watching there. Back to slides. Where did the slides go? Come on. Yeah, so big data network on board. The CCU is the thing in the middle where the ARM processor is. We wrote this, we have so few people. I wrote this thing called Regulus, which is the command and control software. It's a big piece of Java code. Runs on Linux, and 10% of it is sexy, interesting stuff, and 90% of it is what you need to do to stay alive. It's all it's very defensively programmed. We have to deal with anything failing, things failing over, kicking GPS units if they fail, diagnosing problems in the rudder if the rudder is being flaky, trying to decide whether or not you've got like a saltwater incursion in the umbilical, and all kinds of crazy stuff. Is there too much bird poop on the solar cells? There is code for all of that. And inside of it, so if any of you have written web code for an app server like Tomcat or Glassfish. They're written like servlets and JSP pages. This interior architecture is really, really similar, except that it's not, serving HTML. Although I actually do have an embedded web server in there. But it's all about, services that manage the life cycle of all the components. It's essentially sort of booting all the time, and there's this sort of publish, subscribe, interconnect system between all the services. It's really easy to write services and plug them in. So if you want to build a new, this is like the Hello World service. This is one that sends a message to shore if you cross the equator. And it just sort of expresses interest in where you are, and then it sort of listens to the location. LLT is that long in time, and when the sign changes on latitude, it issues a message. Sorry. So there's a bunch of built-in services, and making these things so that they're really, really flexible, so you can plug in all kinds of different devices and behaviors and such, has been pretty entertaining. So one of the whole classes of things in here is about autonomous behaviors. So this has got a what some AI people call a potential field solver, although it's sort of the first derivative of a potential field, so it's forces. And with a potential field robotic control system, what you do is you sort of set up what looks like a field, almost like a gravitational field, and then it's like rolling marbles on a distorted sheet of rubber. So the way that this is set up is it's sort of a flat surface with a channel in it that represents a picket fence. So the task that these wave gliders are supposed to be doing is sort of patrolling along a line. So the little squiggly yellow things are the simulated wave gliders, and they're dropped in the water over here, and they swim over and they figure out their stations. But the actual trajectory planning and adjustment of the trajectories and staying away from each other is all done autonomously by the motion solver. We don't tell them, turn left, turn right, whatever. The goals that these are given is literally, here's a line, stay on that line, get to that line, and stay equally spaced away from your buddies, right? So in this one it's 4, and then the 5th one gets dropped in, and you see how when the 5th one gets dropped in, the 4 sort of spread out, and they do it in a very sort of smooth way. Here's exactly the same scenario, except that the wave gliders get dropped in a different place, and so then they evolve a completely different plan that ends up with the same result. And you see when the 5th one gets dropped in, it doesn't swim to the middle, it then swam to the end, and all the other ones just kind of like nicely moved over. And that's a really nice sort of AI solver that's a part of this software framework. And getting this to work and then to actually like deploy it in the ocean has been a lot of fun. Here's another simulation, and this one involves a ship going through. And you could see when the ship goes through, the one gets out of the way. This one, right, the one that lands here gets out of the way. But because it's then leaving a big gap, if you watch when the ship comes through, this yellow guy, he kind of moves over and gets closer to the ship to try to keep the spacing and the sort of the data meshes as uniform as possible. This actually runs in real life. So this is a screenshot that the guy I know took of a strange and really primitive command and control system used by scary people. But so this is an incident that happened I don't know, a couple months ago. So the X's are positions of a wave glider, and this is 2 wave gliders that we're just sort of marching in a square. When we have nothing else for them to do at our test center, we just have them march in a square. And this black line here is the edge of. We've got a permit from the Coast Guard for about 50 square miles of ocean, where we're allowed to do our testing and evaluation, and people are supposed to stay out of that. But there are some people who just don't care, right? They pay no attention to the Coast Guard, you know. And so this particular ship right here, this was a Navy SEALs training vessel, and they really don't care about the Coast Guard. And they just kind of like meandered through into our test area, and you can see how this guy decided it was getting too close, but he just wanted to keep his distance. So rather than doing the square, he just kind of kept his distance. And then this guy here, because it looked like the SEALs were on a collision course, he did a much more aggressive evasion rather than just a stay away. And we've had, you know, many ship encounters with this over the last 6 months since this stuff has started working, and it's amazing. The software is really good at getting out of the way, and it's probably the single thing that I'm most proud of in this thing is that it does a really good job of getting out of the way. I could rant on about fault management and communications, and none of this really. This is like way too deep. So this is a video of the wing rack running. You probably look at this and say, this is really boring because the rudder is straight. And in actual fact, the rudder isn't straight. It's moving back and forth by about 2 or 3 degrees. And the control algorithms for that I sweated over, because a lot of what's interesting about this is trying to keep the trajectory really efficient. And at one point in this video, it does a little dancing maneuver to try to spin to sort of spin the sub. There you see it's cranking over, and it's actually able to do, you know, pretty tight corners. But I spend a lot of time, you know, in the water just watching the dynamics of these things run. Any software job that involves putting on a snorkel mask to debug your software is a good job, right? I don't care, you know, how little they pay me, you know, being able to do that. And it's been interesting because we do most of our testing quite a few miles offshore, and getting used to being in the ocean when there's nothing. You know, it's 500 feet of visibility and you're in water that's a mile deep. Can be a little disconcerting. And you know, I'm always staring at the wave glider, and we've always got a check diver who's staring at everything that I'm not staring at. And he has a camera and a spear gun, and he deals with the curious critters, and occasionally comes back with lunch. So thanks. I'm willing to answer questions about kind of anything.
If he misses with the spear gun?
Yeah. Let's go with that one. How do we detect ships? Well, the primary and most effective way is effectively cheating. Namely, they all have radio beacons, and there are very strict international regulations on having radio transponders. So we listen for those. If you're close to shore, and for like small boats, like little sport fishing boats, and that they're not required to have transponders. So we do some work with acoustic sensors. Getting acoustic sensors to work reliably is remarkably dicey. And actually, one of the things that makes it doubly difficult is there's this whole set of regulations that are actually almost every country that's a part of like NATO and the UN has what are called the ITAR regulations, International Trafficking in Arms. And it turns out that having good acoustic sensors in the water is really useful for things like submarine tracking. So legally, a good microphone is an atomic bomb. So trying to do ship tracking without crossing the ITAR threshold is entertaining. We're kind of there, sort of, maybe. We're not doing that in production. It's entertaining. Yep. Yeah, so these have all got GPS receivers. Yeah. So we use GPS to know where we are. In fact, I mean, one of the interesting things about GPS these days is it's almost impossible to buy something without a GPS receiver. So we intentionally installed a GPS receiver, and we have 3 more that come along free for the ride. One of the things that I find kind of astonishing about GPS receivers is how inherently flaky they are. So the most active part of failure management on the system is managing the crazy GPS receivers. How fast does it move? So it's got 700 pounds of thrust, so it can pull actually quite a lot. But they don't go very fast. They go about 2 knots. So it's kind of like a pleasant stroll. It's kind of like a hike across the Atlantic. But it never stops, right? 24 hours a day, right? And if you're only doing 2 knots, 24 hours a day makes a big difference, right? And one of the really interesting things is that if you talk to the people who make scientific instruments, traveling at high speeds, like 10 knots, it makes almost all instruments useless. So if you're going to make any kind of a sampling, you have to stop the boat. So you dash along at 10 knots and stop, dash along at 10 knots and stop, because most of the instruments, they'll work okay up to about 2 knots, and then they start failing. So we're about as fast as we can possibly be and still have functioning instruments. So the big ships, they're so expensive, you can't afford to have them travel at a speed that would be effective for the instruments. And just kind of by an accident of physics, we're pretty much the perfect speed for most instruments. So it works out really well. Well, yeah, it's hard to know. They're kind of in the $250,000 range. A lot depends on what you stick on them, and because they're hand assembled by old world craftsmen. They're kind of like a Bentley. That's where most of it goes. But most of the instruments that you would bolt onto this thing, you start bolting interesting instruments onto them, and you can double the price, because they get kind of crazy pretty quickly. And one of the interesting challenges for us is to get effective instruments at sensible prices. And if once we get to reasonable volume, we can drop the price a lot. I mean, it's mostly fairly commodity parts. I mean, there's a fair amount of machined titanium, which, you know, titanium is just hard to work with. And we've gone through lots and lots and lots of flavors of stainless steel, and they just don't work as well. And you know, I don't know how cheap we could get them, but a lot cheaper once we've got volume. But the real cost is the instruments. Yeah, so ocean missions can be a year. You know, I mean, a lot of the reasons that they're that expensive is the materials to make them last that long, right? So if you just wanted to be out there for a week, you could use stainless steel. If you didn't care about surviving a Category 4 hurricane, you could do a lot of different things. I mean, one of the things that I find really interesting is I'm like the chief software guy, but we've got all these weird mechanical engineers and aeronautical engineers and materials guys. You know, probably the single highest tech component that we have is that umbilical, the thing that connects the sub to the float. And you think, isn't that just like a rope with some wire in it? Well, yeah, except, you know, imagine you've got 60-foot waves, 150 nautical mile an hour winds. You blast out through the top of one of these waves, and then you're slamming in, and you get these gigantic shock loads on that thing, and it's got wire in it. So it's not like typical copper wire, right? The wire that's used is really funny stuff. It's got kind of a shell that's kind of like rubbery, and you can stretch the wire, and it doesn't break. It still has the signal still goes through, and if you open up the wire, you find that the wire is made of little like inch-long fibers of copper that slide against each other, and so the fibers all sort of like slide and keep meshing and maintaining a continuous signal path despite all the shock loads, and there's these, you know, crazy flavors of it's actually stainless steel on the other side, and then this weird Kevlar shell, and it's like, fun. Well, so we use pretty much all the standard TCP/IP stacks and such when we're within cell phone range. So we use fairly standard internet protocols. We do somewhat more compression than normal just because it's a cell phone, and we try to get as much stuff off through the cell phone as possible. When we're further out and we're just on Iridium, that we had to completely rewrite, because there are no existing protocols that come close to dealing with that kind of a data rate sensibly, and also the way that there are lots of different satellite protocols. Some of them try to look like the internet. So there's a standard called BGAN, which is used to a lot of the synchronous orbit satellites, and that looks like a serial line, and people run TCP over that using PPP if you ever used that, but you have to change the tuning parameters in TCP because you're going out to synchronous orbit. It's just crazy. And the overheads in TCP tend to like be really expensive, both in time and money. SBD is almost literally text messaging, right? So you give the satellite antenna a packet of at most 300 bytes. Some of them will take up to 1,000 bytes, and you say deliver it, and sometime in the next 25 seconds to 2 hours, it will arrive at its destination. Probably. Right? Sort of like 99%. Right? So error rates are different, delivery times are different. It is such a different networking world that you just have to think about it differently. And that's been very entertaining.
Before I start, I just want to say, we meet again. Last time we spoke, I was a 15-year-old high school student, getting my first computer account from TSS-8, 19-year-old.
Yeah, that was a good job. Yeah. Yeah.
And so it's been 40 years. And I've noticed two things over a whole career, starting in computing until I'm an engineer, went back for a science degree. So my whole career's been kind of like your first job and your last one, where I'm sort of the one programmer surrounded by a bunch of engineers trying to get something done. And it's not about this little sort of programmer, but it's get the result. And the thing I noticed, one is we've been through at least 4 cycles of somebody saying that, or rather, usually a bunch of marketing people saying it's a great silver bullet for generating plans. So, computing ever after when you absolutely never happened. I was wondering if you think you ever will or could.
Nah.
And
No, I mean, you know, the world will always be filled with snake oil salesmen. You know, their goal is to make a buck. My goal is to make something work. They're often, you know, and you know, many of the you know, 4GL or you know, SOA or WSDL or any of the other acronyms that have, you know, blessed or cursed the industry over the years. I find them really trying. You know, particularly like when I was at Sun, we would always have these experiences where somebody like Microsoft or IBM would come up with one of these buzz phrases, hire a bunch of marketing people, blitz the airwaves with this, mostly coded in mumbo jumbo, and then if you try to, and their whole goal is to create fear, uncertainty, and doubt, and get like reporters to go after their adversaries. And so when you get, you know, some clueless reporter from computer world asking you about what your answer to SOA is, you can't actually give them an intelligent answer because they can't parse the sentences. Right? So, I mean, one of the things I feel really bad about over my career is that you get into those situations and kind of all you can do is sort of go along. Right, and then you know you just know that behind the curtain is a charlatan, and you just have to make sure that you're kind of doing the right thing on the side, and you know you always end up with kind of two stacks, right? There's the stack that works, that the customers that come to you and say, you know, we can't make this SOA stuff work. What do we do? I say, well, you don't use it. Use this, right? This is like way faster, way easier to use, way cheaper, and it's politically incorrect, but it works, and it's one of the most tragic dances of being in the computer business ever. I mean, I'm sure it happens in most other industries, but the wheel that spins so fast in the computer business that this just happens over and over and over again, and it's like just, you know, I just get sick of it. You're welcome. You're welcome. Um, I mean, there are a lot of JVM-based languages these days, some of which I'm rather fond of. I quite like Scala. I quite like Clojure. Clojure is a little too weird for most people. Using Clojure correctly is somewhat difficult. Scala is abused by lots of people, but given the group of people that I was trying to work with, most of whom were like C programmers, so that when Java was designed, it was really sort of an intentional fraud. And by that, what I meant was there's all kinds of really interesting computer science solutions to a bunch of interesting problems that have been around for a long time. And high on my list were things like exception handling, multi-threading, garbage collection, that in an industrial setting had a really bad reputation. And bad reputations for stupid reasons, right? So people would say, oh, garbage collection is awful because it means my programmers are lazy, right? I mean, my wife makes me take out the garbage, every week. Why don't you? Right? It's like, that was a really deep and convincing argument, right? And that's what they cling to is stuff like that, because they don't really know what's going on. But there's a long list of reasons why garbage collection is really important, and multi-threading and the rest of it. And I was sort of in this position where there were a bunch of things that we were doing that needed a bunch of these solutions that were, in some sense, pretty standard from an academic computer science point of view, but really incomprehensible to the sort of industrial programmer crowd. And Java was this sort of fraud to, it's sort of a wolf in sheep's clothing kind of deal, right? It was trying to make rocket science look like something comfortable, right? So it looks, for the world of people who were C programmers and C++ programmers, you could show them a Java program, and they'd pretty much get it pretty quickly. I mean, some of the object stuff would kind of spit them loose, but if they had used C++, it would make sense. They would do all kinds of kind of crazy things early on if they were trying to use threading and they had learned how to use POSIX threads. POSIX threads are like the world's worst learning exercise. But I found myself in an environment rich with people who were like embedded device programmers, and they needed the goal was to get something done, right? Not do something spiffy, right? And to try to get these people up to speed really quickly. If I had to teach these folks how to use Clojure, would never have gotten off the ground, because they would have, the heads would have exploded. And in all truth, all of the stuff that's like cool about the way that, say, Clojure and Scala and any of the others work was actually irrelevant, right? The kind of things that we really needed were the large-scale modularity, the multi-threaded, high performance, good security architecture, garbage collection, the ability to do AI kind of tasks, and those were really unaffected by like surface syntax of the language. So it was just kind of the obvious thing. And also I had just finished doing a big Scala project, and Scala had some interesting performance issues that I wasn't willing to deal with in this next project, so I kind of went retro. Other questions? Well, I'm a real sort of Internet of Things fan. I've been giving Internet of Things talks for like 30 years. And, you know, for me, you know, making the world around me more intelligent is just cool. You know, I have a strong bias towards, you know, making my environment intelligent, and I'm you know, in the wrong Myers-Briggs quadrant to find social networking remotely interesting. You know, I'd much rather, you know, talk to people than Facebook chat with people. You know, and you know, find somebody random in a coffee shop in Silicon Valley, and you'll always have a cool conversation.
Thank you very much.
Thank you.
For coming out. So James will probably be around for a few more minutes anyway. So I know there were a few more questions here, which will encourage you to talk. Might be a bit hit and miss, just trying to catch it in the coffee shop. Like that. Weather down there. A couple of things I want to say. I'm going to, on behalf of Terry, thank the Department of Computer Science for, I'm sure, an enormous amount of work putting this thing on. Yes, you can applaud that.
Hey, that's one that I can apply.
I also want to thank the team at Alumni Relations for their help, because they have actually taken a serious engagement this year, and I think they deserve a round of applause. I have no idea what to say at all if it wasn't for my communication team, who actually gives me these notes, so I have the foggiest idea what I'm talking about. So thank you, MH, and for the event. And the final thing is, this one is pretty good. Has anybody in here ever heard of Tom Keenan?
Mm-hmm.
Okay, well, the next event, and we hope you will join us for this, is on April 10th, and anybody who knows Tom will know. Kind of strange stuff at times. We'll
He's
take-
guaranteed entertaining.
He's entertaining, and I'm going to read this. It's priceless. Will take us on a journey through some of the creepiest corners of technology. A journey that is sure to make an hair on the back of your neck stand out. So put that in your calendar, April 10th. I believe
That's a really knowing Tom. That's a scary
Yeah.
description. I would go.
Scary people at one time? Well, Tom's going to bring them here.
Well, no, I was referring to a different kind of scary.